We're looking at alternating infinite series, and this is the third video of this little series of videos, approximations and error bounds. We've been specifically looking at the alternating harmonic series, and we'll continue to do that here. If you remember in the second video, or if you watched it, we were looking at whether or not this series converges. We concluded that it did, and one of the ways that we're talking about whether it converges or not, we started out by looking at these partial sums, which are the sums of the first n terms. So, whoops. So I guess that's actually okay. Sums of the first n terms. So this one was the sum of the first one terms, right? This is, we'll call this S1, right? This is the sum of the first one terms. This is the sum of the first two terms. We'll call this S2, S3, S4. And the idea is any one of these could be an approximation. And if you remember, we were kind of looking at why it converges. If we started at 1, the first term, and then you add in the second term, it brings you down a half, right? And then when you add in the third term, it brings you up less than it brought us down. And then we go down less than we just came up, and so on. And we kind of keep honing in a little closer each time around the exact value of this entire sum. Let's call the entire sum, the whole thing, let's just call it S, okay? And then S1, S2, S3, and S4, they're all just approximations for it. We could really stop anywhere. We could say, well, 1. 1's an approximation for this summation, right? It's not the best approximation. It would be a little better if we go a little bit further. So if we go down to the, minus a half here to get down here, 1/2 is a slightly better approximation, right? That's S2. We could really stop anywhere. So let's suppose that we stop with S4. We could say then that S is approximately equal to S4, right? And again, S is the actual value. It represents the actual value here of the entire series. So we could write that as the summation of the entire thing here from n equals 1 to infinity. I'm going to have to make a little more room here. Of -1 to the n minus 1 times 1 over n, okay, is equal to S, which is approximately equal to S4. So 7/12 is actually a decent approximation for this summation. But how good is it? That's the question. So S4 again is 7/12. And again, we're using that as an estimate, right? If you want to know how good that is, there's a couple ways to think about this. That S4 comes right after we added the fourth term, which was the -1/4. So it's right after this stop right here. That's the 7/12. And if you look at the next term, if you look at the very next term is +1/5, we know that the correct value for S is somewhere in between here. So it's definitely within that 1/5 of our estimate, 7/12. So what we can say, and this is the alternating series error bound, S4 is an approximation for the series. So for S, which is the series value. And the difference between S and S4, let's put absolute values around that because it doesn't matter, if we're at an overestimate or underestimate here. This is the exact error then of our approximation. The error of our approximation. It's called the remainder also. Because of that, we can call it R4. And again, we can throw absolute values on this. And the idea is that R4 represents the remainder. What's left of the series when we stop, right? So if we took the fourth partial sum, we took those 4 terms, and then R4 is everything else combined. It's the rest of the infinitely many terms there added together, right? That's the error. That's how far off we are from the exact value. So we can approximate. I guess I could leave that here. This is S4. The rest here is R4. And again, the whole thing, of course, is S. And so what we want to do is say we know that this error is, we don't know exactly what it is, right? Then we would know what the series value is, but we know that it's definitely less than, or well, less than or equal to, let's say, that next term's magnitude, right? That's what we know, because then we're going to come back again, not as far, and then we're going to go up again, not as far again. So we know that we're for sure within that next term, which in this case is 1/5. So if you want that error bound, then we need to use that the next term. So since we're doing R4, then we're going to do the fifth term. If this whole thing is A sub n, the terms of our series here, of our series, yeah, then what I want is A sub 5. And again, I'll throw this in absolute values. So we're not paying any attention to the sign of this, whether it's positive or negative. Um, we are simply saying that the magnitude of the error, right, or of the remainder, if you want to think of it that way, the magnitude of that, this is the same thing as this, and that magnitude is definitely no bigger than the next term. That's what this says. Whoops. So here, let me throw those on there again. This is the next term that was unused in the sum, and it is our error. Whoops, I can't spell. The next term, and it is our error bound. All right, so this is just a little bit of the notation here too, makes this tricky, but again, if you have a convergent alternating series, that means it will be changing signs with every term, and it'll be decreasing in magnitude towards 0, which means you can really stop anywhere. Use that as an approximation. Here we stopped at S4, and you can say that the magnitude of that next term is the error bound.